However, if you're working with an underpowered battery-operated device, you're going to spend significant time in this green entry region. And if you look and break the error out for just this region alone, this is where we see our model really outperforms the industry standards.
Hi, and welcome back. I'm Ron Miller with FPrin LLC. I'm here to relate some new information that we have on some very cool capabilities that have been recently developed at FPrin LLC, specifically regarding a new model that we have to look at SMA wire actuators and how to better model their response, particularly in low energy environments. I have with me Lawrence Smith, who is one of the engineers and really the main architect of this new model. Lawrence, how are you? Can you just introduce yourself really quick?
Of course. Yeah, thanks, Ron. I'm doing well. As you said, I'm an engineer at FPrin, and I was one of the originators and architects of this model, and I'm looking forward to explaining, what it does, why we want to develop it, and then how it could be useful to you.
Yeah, fantastic. Thanks, Lawrence. Before we get into the model itself, can you just explain for the audience what an SMA wire actuator is?
Right, of course. So this is a particular alloy that exhibits some really non-intuitive mechanical response, whereby when it's heated, it transitions between two crystalline phases and then undergoes some macroscopic strain recovery. So this basically means you can take a piece of wire, you can stretch it out, heat it up, and it will contract back to its original length. And the force that it can contract with is very, very high relative to its weight. So it's very power dense in terms of mechanical power density. So these are really useful in space constrained and cost constrained applications, but they're tricky to use and they're very tricky to model numerically.
Where would you use an SMA wire actuator in a medical device, per se?
Yeah, so think of any time that you'd want to convert stored electrical energy into output mechanical work.
So tell me about the new model. It's kind of a mouthful, but we're calling it an asymmetric rational piecewise model, or APR for short. Maybe you can describe what those three words together mean. And then also just talk about the rationale for coming up with a new model. Why do we need it as opposed to what's out there already?
Of course, yeah. So it is a little bit of a mouthful, but that mouthful just describes the constitutive mathematical relations that define the shape of the transformation curve. That we'll look at this when we look at the slides, but the way in which the wire transitions between crystalline phases is not just like a straight line. It actually has a kind of a complicated shape. And so asymmetric means that it's not symmetric about the center line. Rational, our model uses a rational expression. And then piecewise, it's a construction of multiple different curves to really precisely replicate the shape of that transformation curve that we observe in experiment. But I think it'll make more sense when we look at plots.
All right, Lawrence, I think the next thing to do here is just to go over the executive summary. If you can just walk us through how you went about coming up with a model and how you went about confirming the model. And then I think we have some data that we can go over as well, which would be pretty exciting. And also a look at the test jig that we use to go ahead and confirm the coefficients that need to go into the model. I'll let you take it away.
Yeah, so some highlights in this presentation, I'd like to go over how we actually extract coefficients that plug into our model using real tests on real wire, what the model actually looks like, and how it compares to existing approaches. And then finally, how accurately we can predict the behavior that we observe in our experiments when we overlay simulated results. So we, in addition to kind of developing this mathematical model, we also developed a thorough mechanical test rig, which allows us to put different alloy blends of wires, different lengths of wires, different diameters through prescribed temperature and stress versus time profiles. These can be like really simple, like maybe ramping temperature up linearly while holding stress constant, or very complex. We can do cyclic loading, partial transitions, and all sorts of other kind of more exotic boundary conditions on our wire. But the point is that we've got a wide range of testable options. Anything that you would see in a micro electromechanical device, diameters 2 millimeters and below, usually pretty far below, and then temperatures up to 100 Celsius, which is usually well above the region of interest for these food wires.
Great, Lawrence. Maybe we can move to the slide that shows the test rig, and you can explain not only what the components of the test rig are and but more importantly, what you use it for and the outputs of the test rig and how it helps to inform the model.
So I've got our thermomechanical test rig picture on this slide with some of the main components listed out. The kind of most interesting piece is the shape memory wire itself, which is almost invisible. In fact, I think it's under 100 micron in diameter in this image, so it's very hard to see, but it's stretched taut between the two vertical plastic pillars that you kind of see, these peak rods. And then that's the core of the fixture, and everything else kind of supports that. So there's essentially a bathtub filled with oil that can sustain high temperatures without boiling, that can be raised and lowered in order to submerge the wire. And then we've got a closed loop heating and cooling system that can both electrically heat this entire bath at whatever rate we'd like, but also pump water through the bath to cool it if the temperature is getting too high. So we've got like a closed loop thermal system that controls the oil bath temperature to these prescribed temperature versus time profiles. And then we've got this one fixed rod and a rod mounted on a linear bearing that we can load with a force, essentially by hanging a mass over this pulley. And so we know exactly the force with which we're pulling on this carriage that's stretching the wire top. On top of that, we're actually also measuring that force in series using this load cell. And the final piece of the puzzle is a extremely accurate non-contact magnetic linear encoder that essentially reads the position of the wire over time. And that's how we decide and analyze how much strain the wire is seeing.
So then the output, Lawrence, of this rig gives you what information?
Right, so this rig is designed precisely for one thing, which is to extract a curve. It's a curve of volume fraction of one of the phases against temperature. And this is the exact curve we're going to look at in a moment. So we designed this fixture to do one thing very well, which is to extract a unique curve that describes the shape of the transformation between two phases. And that curve is essentially volume fraction against temperature. The curve is unique to any specific alloy of shape memory alloy, which there's multiple, and it kind of is unique to a specific blend. So this essentially helps us characterize really precisely the shape of that transformation curve. And we can actually look at some of these data in a moment if you'd like to.
Lawrence, just to kind of put this in terms that I can understand, you basically use this test rig to go ahead and form a different curve, fit a different curve to each different wire alloy and potentially diameter too. Is that correct?
Exactly. So we're trying to extract like this fundamental transformation behavior that's unique to any particular wire.
Let's get to some data.
So on the left here, these red circles are these data that I just mentioned. So we've got on the x-axis the temperature of the wire, and on the y-axis we've got the volume fraction of one of the crystalline phases, which starts at 1 and ends at 0 as you transition from phase A to phase B, right? These two phases are called martensite and austenite. But essentially you can see that this line is not just a diagonal line that crosses from one endpoint to the other. It's got this really interesting kind of S shape to it. So these red circles are essentially the data that we gather off of our test rig. The question is, when you want to implement a numerical model that explains the change in phase as a function of temperature and applied stress, how would you actually describe the shape of this data? And so there are a multitude of ways of doing this in literature, ranging from the simplest to the most complicated. And maybe the simplest would just be to say, well, why don't we just fit a straight line to the region with the highest slope? That's what I've done here in the leftmost in the leftmost is that, what if we just imagine that, this wire doesn't transition at all until it hits this MS, this Martensite start temperature, and then it zips down along this straight line to full complete transition. This works really well right in the center line region, right around the center of the transition, but it's actually very poor at predicting what the wire is actually doing in the entry and the exit regions. You can see like a large deviation from this blue line and these red dots. So what we're looking at here in the center plot is just a variety. So this is like 4 different ways of modeling the shape of this curve. And we're looking at the error between the experimental data that we collected and the data that the model would predict. And you can see that there's large spikes in error near the entrance and exit of the transition. And so what we do after we collect data is essentially perform an automated curve fitting algorithm in order to extract the coefficients that plug into our model to minimize the error between the experimental data that we gather and then the simulated response that the model predicts. And so we can do this by, for example, minimizing this included area that's shaded in green here between the input data and the model prediction. On the left-hand plot here, what we're looking at is some data that we actually gather from our fixture in these red circles. So on the x-axis, we're looking at the temperature of the wire. On the y-axis, we're looking at the volume fraction of one of the phases. So we begin with a volume fraction of 1 in the upper left corner, and we end with a volume fraction of 0 in the lower right corner. And as you can see, the shape that we observe in our experiment is not just a diagonal line that connects these 2 endpoints. It's something more interesting, this kind of S shape. I've overlaid on this a popular, widely used model called the FPrin model, which essentially attempts to mimic the shape of this curve using a cosine wave. And you can see that in the center of the transition region, it does an all right job. But in the entry and the exit regions of the transformation, there's actually a large amount of local error. And this is really important because for these disposable electromechanical devices that are usually underpowered and battery operated, you're going to spend a lot of time in these entry and exit regions. It's, up to 40% of the total transformation we added up. And if you don't know what's going on in these areas, you're going to actually run into trouble when you're trying to model your device accurately. And so we developed the ARP model precisely in order to follow the shape of this curve better than this FPrin model, for example. If we look on the right here, what I've done is just computed the local error. So if I subtract what we observe in experiment and then what a different model predicts, we get an error measure. Of course, we'd love to see a flat line at 0 where this dash is. That would mean that the data and our model prediction are totally coincident and there's no error at all. But the thing I'd like to highlight is that if we go and kind of zoom in on certain area of the curve, our blue line here, which indicates this ARP model, exhibits much lower error than these other models used widely, in literature, especially in these critical entry and exit regions. And so we find lower error overall compared to existing models, but especially much lower error in the critical regions for the specific application we're looking at, these small battery-powered devices.
Fantastic. And I think you have another slide that shows the accuracy breakdown in even more granular form. Why don't we go over that now to show the audience exactly what you're talking about?
Of course. Right. So what we're looking at here is just like a single trial. And you might say, well, how repeatable is this? So we actually did some experiments where we tested 60 different wires under different stretch conditions, different lengths, diameters, wire blends. And we computed for every single wire, both, that we gathered experimental data, and then we computed error over our model fit for the ARP model that we present in this work. Also the FPrin model, which is kind of the industry standard. And what we see when we look at the total sum squared error between simulation or model and our observed data is that we have much lower error. So of course we love to see one bar that's centered over 0 error. That's great. I mean, like every single wire showed no error at all. Instead, we see this kind of statistical distribution of error, which is a lot tighter and a lot lower in magnitude when you compare it to the red distribution, which is the Brinson model. But to look even more granularly, where does that error come from? If you break it down into kind of 2 different regions, so I'll call it an entry region, that's highlighted green here, and then a bulk region in blue, you can see that actually both models perform pretty well in the bulk region. So they're, I think, both suitable to use if you are guaranteed to stay in the bulk region. And I would say that actually both models are suitable if you're not power constrained and you're guaranteed to fully transition every time you actuate your wire, because you're going to be in this bulk region for a majority of the time. However, if you're working with an underpowered battery operated device, you're going to spend significant time in this green entry region. And if you look and break the error out for just this region alone, this is where we see our model really outperforms the industry standard. So outperforms means the average, the mean error is much lower by a factor of 4 or 5. The distribution is also a lot tighter. And this is extremely critical because this is the area of interest for our application.
That's pretty stark data there.
So to wrap it all up, we can look at a plot that kind of captures everything that I've laid out in the last couple of slides. Right here, we've got the data we collected off of a single wire on our test fixture, shown with these black circles, and then the solid red line that just very closely traces the shape of that curve in this critical bulk region, but also in these just as critical entry and exit regions. That's kind of the shape of the curve predicted by our model. You can compare that to the Brinson model prediction, which, as I kind of laid out in a statistical way a second ago, just is not able to both capture the bulk behavior and the entry and exit behavior. And as you can see, the main benefit of our model is that it's extremely tunable. So you can think of this as a number of coefficients which act like knobs that we can turn up and down to control independently the location and the steepness of the curve in the bulk region, but also the curvature of the entrance and exit regions. And actually, we can control this independently. This is kind of the asymmetric part of the model. The fact that it's piecewise means that we can construct it from smaller, simpler curves to make a complicated, asymmetric shape, which actually mimics the complicated and asymmetric relationship we see in our actual data. And so at the end of the day, basically, we can take any alloy blend of wire, we can extract some empirical data, and then we can do automated curve fitting in order to find the set of coefficients we plug into the ARP model so that we get a really high fidelity, flexible model of the transformation, so that when we go and implement this wire numerically in a system level model, say of a medical device, we can be really confident that we're actually predicting that behavior that we'll see in real life.
I think that's fantastic, Lawrence. Thanks so much for describing the model and how you went about doing it, the motivations for doing it, and the benefits for doing it. I think it's also important to comment on the fact that this is a computationally efficient approach. It's fairly easy. We're being fairly open source with the way to go about doing it. We have a white paper that's available that we will share with whoever desires. You can find this white paper on our website as well. That kind of goes into much more detail about how the model works and how it was developed. We look to share this with as many people that would want to use it, being an open source model, and we can help to refine that model to your specific application, your specific alloy. We'll go ahead and put the URL on how to get to the white paper. I think that's about it. Anything else you'd like to add before we sign off?
No, I think that we've covered most of the highlights pretty well here. So yeah, we look forward to working with anyone that's curious about either implementing shape memory alloy actuators in their device, or possibly refining their numerical models of their device to include this the behavior that they maybe observe in tests but are not able to model on the simulation side.
Great, Lawrence. Thank you for your time. And audience, thank you for your time. If you're interested more about this model and what it can do, please click on the link below, and we'll provide you the information as soon as possible. And we can always set an appointment up with you to discuss what the model is and its benefits and how it can be of service to you. Thank you, Lawrence. Thank you, audience. Have a great day.